This is a run through the Rates and Equilibria test, so please have a look through this and compare to your answers. Right, so first one's a practical question about a student who investigated how concentration affects the rate of reaction between magnesium and hydrochloric acid. And then we got various information about that method. So here's your method: hydrochloric acid in a flask, add some magnesium, collect in a gas syringe, the gas produced, measure the volume, repeat, change the concentration. Right, you've got to go for some control variables. Now, in this particular case then, you've got various things you can go for. First up though, let's just identify the other types of variables. So you've got the independent variable, which is the thing you change. So they are changing the concentration, so therefore this becomes the independent variable. The dependent variable is what they measure, so they are measuring the volume of gas. So that's your dependent variable. And therefore control variables are things that are going to affect the reaction rate and therefore must stay the same. So you should be aware that things that affect reaction rate are temperature, pressure of a gas, concentration of a solution, and addition of a catalyst, and surface area of a solid. So in this particular case then, so the concentration is the thing that we're changing, therefore all the others need to stay the same. So we need a constant temperature. If there was gases involved in the reaction, we need a constant pressure, but obviously we have a powder and a solution. Obviously concentration is the thing we're changing. Catalyst, there's no catalyst used, so that's not really relevant. Surface area, well, we've got your magnesium powder here, so they've talked about powder, but we need to make sure that will stay the same. So let's have a little look at what we've got. So, mass of magnesium powder. Right, the mass, you might think, well, hang on, that's not in this list. But of course, if there is more of the powder, there would be a larger surface area because there's more of it. All right, so therefore, you have a faster rate. So you've got to keep the mass the same. Temperature, that's on our list. And the other two, time and volume of gas collected, well, that's a dependent variable. And that, of course, is linked to the concentration. So the higher the concentration, the quicker it would be. Right, question number 2. So these ones are a little bit confusing, some of these graph ones. Hopefully this one wasn't too bad, but let's have a bit of a look. So no calculations, that just means that essentially we don't want any of the other stuff because the answer won't pick it up. So I know it's quite difficult on my little version here, but hopefully you can see that it tells you that the mean rate of reaction is the mean volume of gas produced over time. Now, you're really going to expect it to know that, but we popped it in here anyway. They're looking for between 0 and 50. So 0 and 50 is there. So basically what you have to do is to go up to this point, right, and then read across, and you will see that we have 80. So therefore, if it is the volume, so there's 80 produced in 50 seconds, it's going to be 80 over 50. So if you wrote 80 over 50, that was okay. If you wrote what that equaled, which of course was whatever it was, 1.6, that was okay, or 1.60. So no worries there. Next one. So question 3, where are you? Here we go. Right, question 3 is this one. So this is the first one of these ones with the little triangles on. Now I do appreciate these are a little bit confusing, but hopefully it was okay. So we were measuring the rate of reaction. They've drawn a tangent, so they've drawn it here. So obviously in an exam you'd have to do that yourself, but we've done it for you. And then use the triangle to calculate the loss in mass. Right, now if you're just looking for the loss in mass, this is not asking for the reaction rate. It's not asking for a gradient. So the loss in mass, all right, from this triangle, we're talking about from here to here. All right, so we are talking about 1.1, which of course would be there. Take away whatever that is. Now this is open for some debate here. So what's that? 0.72, 0.73. Now, if you do 1.1 take 0.73, obviously you will get 0.37. Now, I then decided that there was a bit of a range going to be allowed on that one. So the range that I allowed was, what was the range I allowed? 0.38, 0.37, 0.36. Right, so that was the kind of range I allowed on that. Right, the next part, so it's looking at the same graph, asks for, blah, 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 tangent drawn, work out the time taken. So this time, they were looking for this value, right? So the X value, so you had to have a look here. Now, common mistake that you're going to make is to go for something along the lines of 126.5, but notice the scale down here. Each of these is 5. So I reckon, right, if you were to look at that, you are going to end up with something that is more like 134, if you have a look in there. However, I allowed 134, 133 or 135. So one either way. All right, so that I reckoned was coming at 134. Now, final part, well, not the final part, sorry, but the next part, number 5. So we've got to use previous 2 answers to calculate the rate. Now, I appreciate if you didn't get those right, then you weren't going to get the rate. So when you actually do the divider on those, so rate is obviously going to be y over x, so grams per second, it's going to be 0.37 divided by 134, which is going to give us 0.003. So 0.37 divided by 134, 0.003. Right, so that was your answer for that one. It then says, what does it say next? It says, blah, 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 number 6, what are the correct units? Right, whenever you're working out units, you've just got to use the axes. So there should be, all right, sorry, if we work out units of something from a gradient of a line, you use the axes. So because the gradient is worked out as y over x, that means the units will be the units of y, which is loss of mass in grams, the units are g, divided by the units of x, which is s. So it is grams per second is your units. That is your answer to number 6, grams per second. Okay, so then we were on to a couple of just kind of learn it jobs. So minimum energy for a successful collision, that is just the definition of activation energy. You've just got to learn that, I'm afraid. Right, just as a quick recap, of course, what I mean by that is, it's this business, isn't it? There's your graph of an exothermic reaction. Here's your reactants. They've got to have that amount of energy when they collide to actually turn them into the individual atoms. Right. Number 8, a reaction produced 88 centimeters cubed of gas in 2 mins. Calculate the average rate of reaction in centimeters cubed per second, 3 sig figs. Surprise number of people fell into trap number 1, as in didn't convert minutes to seconds, or trap number 2, didn't read 3 sig figs. Right, so when you actually do this, first thing you've got to realise is 2 minutes, of course, is 120 seconds. So therefore your sum should have been 88 divided by 120, and if you do that, I believe it will give you this. And there was another option of 0.73, which quite a few people went for. 3 sig figs, of course. Sig figs, you start from the first non-zero number, so 1, 2, 3 sig figs. Units not required, so there you go. That was number 8. Number 9. What's number 9? Oh, that's not number 9. Let's try the other sheet. Number 9 is number 9. Right, so number 9 is this one. What would be the correct method of measuring the rate of reaction below? The equation is shown. Right, now this one was in something like C8.3, I think, when we looked at temperature. This stuff is sodium thiosulfate, that hydrochloric acid. Now, it is very, very tempting to go for something involving this. But if you've looked at that lesson, you should remember that this stuff is pretty soluble and there's not a great deal produced. So you don't actually see any bubbles. That's of no use to you because it just dissolves straight back into the solution. So whenever you have a solid like this, right, then that's the one where you have to basically do it in conical flask. There's my conical flask, right? And then you put a cross underneath. There's my cross on a bit of paper. And you wait until the solution turns cloudy, or if you like, you can't see the cross anymore. Now that, of course, is known as the disappearing cross. All right, so if that is something that is a little bit of a mystery to you, do go back and have a look at whatever I said it was, 8.3, the temperature one. There's a couple of videos on there to look at as well, which actually show the reaction. This one actually is a required practical, so it is important that you know that. Number 10, there are more particles in a given volume, so the number of successful collisions is greater, is the correct reason. Y increases and what increases rate. Okay, here's volume 1, here's volume 2. What's it saying? There are more particles in a given volume. There's some particles. There's some more particles in the same volume. What have you increased? Well, you have increased the concentration or the pressure, depending on whether you are talking about a solution or a gas. And therefore, if you look at your options, you will find that it is increasing concentration. Right, number 11. The graph shows the mass of reaction, or a graph shows how the mass of reaction mixture varies over time in the reaction between calcium carbonate and hydrochloric acid. Which would be the correct way to measure the initial rate? Okay, the key thing here is this. Right, we do not want rate at a specific point, right? So loads of you went for draw a straight line to indicate the average slope and work out the gradient, and that would be to work out the average rate. Initial means at the start. So therefore you need to draw a tangent at t equals 0. What do I mean? Well, if you've got something like this, and you're trying to work out the average rate, then okay, you just go, right, average rate after 100 seconds would be, let's whack a straight line in, as you said, right, and just do volume divided by time. Initial is at the start. So at the start is here. So you would have to draw a tangent there, drop it down, and then do your y over x. Again, I have gone over this in previous lessons, so do have a look back if you're not too sure about that one. Right, what do we call a reaction where the reactants can reform the products? Okay, so this is nothing too clever here. Right, don't be lured into writing equilibrium. This is literally just a reversible reaction. All right, so that's when you get one of those signs. Which two features of a dynamic equilibrium? Okay, 2 boxes. Now this one, check back on your answers because the auto marking wasn't doing a good job on this. It only picked it up if you got both right. So things that you should have gone for are the forward reaction equals, so the rate of the forward reaction equals the rate of reverse. Right, so rate forward equals the rate of reverse. That's one feature. The other one is the concentrations remain unchanged. So concentrations remain unchanged. Now, this is just stuff you've got to learn. The other one, if there was for a third one, would be in a closed system, by the way. So those are the 3 points that you need to learn about what dynamic equilibrium is all about. Then we have our ones where you had to try and apply some Le Chatelier's principle, which is the classic thing of do something to it and it does the other. So let's have a look at these then. Production of methanol, forward reaction is exo. Okay, fine. So that's endo. Which 2 statements are true when the temperature is increased? Okay, so statement number 1 says the rate of reaction is higher or faster. That is true. The rate will always increase if you increase the temperature. Then it says the rate of reaction is slower, so it's obviously not that one. Then you've got 2 about the yield. That's this stuff, remember. So remember, if you do something to it, it will try and do the opposite. So therefore, if you heat this up, which is what it's saying you're doing, it tries to go in the endothermic direction. So the amount of ethanol will go down. So those were your 2 there. Again, the auto marking was a bit rubbish on that. So do check, you may have got an extra mark that I've given you. 15. This one's obviously talking about the pressure. All right, some don't really care that the forward reaction is exo. 2 statements are true when the pressure is increased. Right, let's read through them again. So statement number 1 says the rate is faster. Again, this will always be true. Why? Well, because there are more particles in a given volume, so there are more successful collisions. So the rate will always be increased if you increase the pressure. So therefore, we know that the second one is not true, so we're going to ignore that. Then we got something about yield. Does it get higher or lower? Well, if you're talking about pressure, you need to look at number of particles. There are 1, 2, 3 on the left. There is 1 on the right. Therefore, if you increase the pressure, it will try and do the opposite, decrease it, so it goes to the side with the least molecules, and that, of course, means it goes to the right, so the yield will increase. Right, finally, the industrial questions. Bit of an iffy one, this one. I just sort of made it up, so you might want to argue with me, but this is what I was thinking of. So it says, reactors are often not run under these conditions, all right, to give the highest yield. So there must be a reason for that. Now, the idea is you have to look at the one that is not a reason. So let's go through them. Number one, costs might be too high when compared to the profit made. That sounds like a pretty sensible thing, right? So that very much is a reason why they don't run like that. Second one, the rate might be slow under the conditions required for a high yield. Now, this is really common, all right? So this, again, is a reason why they don't run it. If you look at the ones above here, right? So this one is a classic example. If you heat it up, rate's faster, brilliant, but yield decreases. So that's really common. The reactants might be expensive. Well, actually, believe it or not, that was the correct answer, because actually in the industry, you're pretty worried about whether things are expensive or not. So reactants are expensive, and also it is not linked to the conditions, is it? Right, so that is not a reason. Right, so it is true, but it is not a reason that they don't run it under these conditions. And then finally, it says a catalyst is used to reduce energy costs. Okay, well, that obviously is another reason why they run it under the non-optimum conditions. So I appreciate that last one was a bit confusing, but there we go. If you've got any questions about any of this, do ask, because obviously it's quite tricky to run through in this slightly, dodgy way. I will, I'll respond to any questions you've got, and do check your scores, because you may well have found they go up because the auto marking wasn't great.